Welcome to part B of lecture 14 on graph theory. In this lecture, we will solve some problems related to graph connectivity, more specifically two connected graphs. So, let me start with the first problem. Problem 1. Find the smallest three regular graph having connectivity one. So, you try to construct a graph which is three regular. Three regular means every vertex has degree 3 and connectivity 1. That means you need to remove at least one vertex from the graph to make the graph disconnected. You try to construct such a graph and then look at the solution. So, here is the graph. So, it should be three regular. Now, you can see that all these vertices are having degree 3 and this side also we just replicate the same subgraph here. So, now you can see that this graph is a three regular graph, because every vertex has degree 3 and you need to remove one vertex. So, this is a cut vertex basically. If you remove this vertex or say this vertex, then the graph will become disconnected. Okay. So, the connectivity of this graph is 1. So, this is the first problem. Let us consider the second problem. Problem 2. Prove that a simple graph G is two connected if and only if for every triple x, y, z of distinct vertices G has a xz path through y. Okay, so we know that a graph is two connected if and only if between every pair of vertices there are internally disjoint paths. But this is a different characterization. It says that for every triple x y z and x y z are three distinct vertices, then G has a x z path passing through y. Okay. Since G is two connected, we know that then any two vertices x and y lie on a cycle. Say C1, and similarly YZ lie on a cycle C2, and these two cycles C1 and C2 have at least y in common. There could be more than one vertices common between these two cycles, but at least one vertex y is common. So, let me draw C1, C1 is passing through x and z. So, this is sorry x and y, and C2 contains y and z, right. So, this is C1, this is C2. Then we can say that there is a xz path passing through y, and we can see that path, right. So, this is one possible xz path. So, x to y and then y to z. So, this is one possible xz path that is passing through y. Now, so we have proved that if two is graph G is two connected, then for every triple x y z of distinct vertices, G has a xz path passing through y. That is what we proved just now. So, this is the if part. The only if part is that G is, so you are given that now that for every three triples x y z of distinct vertices, there is a xj path passing through y. That means, for every pair of vertices x z, there is a path which is passing through y, which is not required at this moment for my purpose. There is a path between x and z. So, G is connected, I can say, because between every pair of vertices x z, there is a path between x and z. So, G is connected as there is a path between every pair of vertices. Now, suppose that G has a cut vertex, G has a cut vertex V. That means, if you remove this V from the graph G, then the graph will become disconnected. Okay. So, let x and y be two vertices in two different components of G minus P. Okay, so this is a proof. This part we are proving using contradiction. Okay. So, for x, y and v, these are three distinct vertices in the graph G. There is a x v path through y, because that is what it says, that for every pair of three distinct vertices there is a x z path passing through y. So, there is a path from x to v passing through y. So, this implies that even if you remove this v, the vertex v from the graph, there is a x y path in G minus v. So, x and y must be in the same component of G minus P. So, this is a contradiction. So, this is a contradiction to the fact that we assume that V is a cut vertex of the graph G. Hence, V cannot be a cut vertex. So, G is too connected. Okay. So, in the only if part of this proof, what you are given that for any three distinct vertices x, y, z, there is a x z path passing through y, and then you have to prove that if this is true for a graph G, then the graph is too connected. So, this is a proof by contradiction. We assume that there is a cut vertex V. If there is a cut vertex, then the graph is one connected. And finally, we prove that there can't be a cut vertex in the graph G. So, the graph is not one connected, it is two connected. Okay. So, next we move to the other problem. Problem 3. Let G be a connected graph then you construct G prime from G by adding an edge with endpoints x, y whenever the distance between x and y in the graph G is equal to 2. Okay. So, this is how you construct G prime from G, then you prove that G prime is two connected. Okay. So, two connected, you have to prove that G prime is two connected. That means, there does not exist a cut vertex in the graph G prime. That there does not exist a set of one vertex whose removal disconnect the graph. So, let us look at the solution of this problem. Since this is a connected graph with number of vertices at least 3. Okay. Since n is greater than or equal to 3, it suffices to prove that G prime has no cut vertex. Let x be a vertex of G prime. Okay. If G prime minus x is disconnected, then G minus x is also disconnected. Okay. This is true because G prime has more edges than G. G is basically a subgraph of G prime. Let U and V be in two different components of G minus x. Okay. Now, since G is a connected graph, G is connected, that is what we are given at the beginning, G be a connected graph. Since G is a connected graph, there is a UV path passing through x. This is true because of the fact that we can say that there is a UV path passing through x, because if you remove x from the graph G, it's become disconnected, that is why. Okay. So, there is a UV path U to V which is passing through x. Okay. Now, let A and B be two adjacent vertices of x on this path. So, that means A is here, A is adjacent to x, this is A, and this is B, B is another vertex which is adjacent to x on this path. Okay. Then you see that the distance between A and B in the graph G is equal to 2. Okay. So, A and B will be adjacent in G prime. So, in G prime, these two will be adjacent. Okay. So, it follows that g prime minus x is not disconnected. So, that means x is not a cut vertex in G prime, right, and x is arbitrarily selected. So, there is no cut vertex in G prime, hence G prime is 2 connected. Okay. So, we will talk about another problem now, problem 4. We have seen the similar problem before also. Prove that the edge connectivity k prime g, that is the minimum number of edges that need to be removed from the graph to make the graph disconnected, is equal to kg. Kg is the minimum number of vertices that need to be removed from the graph to make the graph disconnected. This is the vertex connectivity and edge connectivity. This is equal to, the edge connectivity is equal to the vertex connectivity when G is a simple graph with maximum degree less than equal to 3. So, we have proved a similar result for when G is simple 3 regular graph, then k prime g is equal to k g, and then proving if this is true for 3 regular, then this is also true for graph, simple graph with maximum degree 3. The proof or the solution is the same solution. I just outline the solution. Let S be a minimum vertex cut of G. That means, the cardinality of S is k g, and what we know that k prime g is always greater than equal to k g. This is always true, that we have proved at the very beginning. Now, to prove that they are equal, to prove k prime g less than equal to k g, we need a edge cut of size this much. and let similarly that H 1 and H 2 be two components of G minus S. Now, if you remember our previous proof that, so this is what the S is, and if I remove this S, so it consists of some vertices. If you remove this S from the graph will be left with two components H 1 and H 2. Now, we know that since S is the minimum S cut, every vertex V in S has a neighbor in H 1 and a neighbor in, at least one neighbor in H 1 and at least one neighbor in H 2. Now, this graph has degree maximum 3. So, it can be like this. The other situation could be the similar thing we proved for 3 regular graph. This is another situation. It could be like this also, one vertex here, one vertex here, because it is not a 3 regular graph, it has degree maximum 3. So, this vertex has say degree 2, and the other situation could be like this. Now, the idea is that so suppose the vertex cut has 1, 2, 3, 4, 5 vertices. Now, I have to construct a edge cut of size 5. So, what we do is that we remove this edge, and in this case either you can remove this edge or this edge, no problem, and in this case you have removed these two edges. Now, you can see that if you remove this edge, these 5 edges from the graph, there is no path between a vertex in H 1 to a vertex in H 2. So, the graph become disconnected. So, what we got? We got a edge cut of size cardinality of S. So, this proves that K prime G you can construct starting with a vertex cut of size Kg, you can construct a edge cut of size the same size. So, this is true, and then combining this and this, combining this and this, we finally prove that K prime G is equal to Kg. So, what we have proved in the last problem is that if G is a simple graph with maximum degree 3, then the edge connectivity is equal to the vertex connectivity. That is all from graph connectivity. Thank you very much.